And we move to Rodrigo Ferrer-Chavez from Northwestern, talking about exoplanet direct imaging via differentiable instrument models.
Okay, can people hear me? Okay, hello, my name is Rodrigo, and well, let's talk some more PSF subtraction, right? But I want to point something out first. And what I want to highlight throughout this talk is that the problem of PSF subtraction is a physics problem, not only a data analysis problem. The speckles are there, the starlight is there to begin with because instrument aberrations are there that we haven't corrected. So what I want to argue is that if we keep this in mind throughout our algorithm development, we can get very far. And I will show some results in the second half of the talk that put this to the test. So let's talk about what goes wrong usually in PSF subtraction. Now, everyone hates PCA now, right? But let's say that we don't, you know? And let's say what goes actually wrong with it, but in a more fundamental level. First, we have a science observation, right? And this is an example of a real observation from JWST. This is what the PSF looks like on JWST NeuroChem coronagraph. The way to remove this is that you have a set of reference observations, right? For JWST, it's mostly references of images of different stars, right? And then you combine those via apparently PCA, right? And then you build a starlight model, and then you subtract that from your science image, and ideally you would see a planet or a disk or like a clean subtraction. But what you get oftentimes is just a tragedy, you know? And any of these could be a planet or none of those could be a planet, you know, we'll never know. So what goes actually wrong at the physics level here? So when you get your science observation, you get an image not just of a star, but of your entire instrument pretty much, you know? You have certain, I don't know, misalignment between the coronagraph and the star. You have some tilts in the mirrors, the primary mirrors. You have some internal aberrations that might change in some timescales, right? So all of those aberrations, I will call these generally aberrations, are what influences what your image will look like in your detector. But instruments are not perfectly stable, right? So by the time you take your reference observations, those aberrations will have changed. So your PSFs will have changed, and you cannot get a perfect subtraction from them. And this is why, you know, like the telescope stability is like the boogeyman now when talking about like HWO and all these things. Because if we want to get to the point where we can image exo-Earths, we might as well keep this like as stable as possible, and that is pretty hard. So how do we figure this out? This is the first point I want to highlight, that instruments are not perfectly stable, and that if we do not account for this, we will never get it a perfect subtraction. And the second point is related to that, is that traditional PSF subtraction, basically, you know, like PCA or other related methods, basically leave a lot of physics on the table, right? Again, we know what the instrument is, we have waveform sensing data and all these things, and we are not using them. We might as well be PCAing images of trees or something, and PCA can also do it, you know? So we have a lot of things that we have put into developing these instruments, we might as well use it. So starlight subtraction is a problem of uncorrected aberrations. So the most natural thing to try is to correct for those aberrations. This takes us to model-based PSF subtraction. We have our science instrument and, you know, our aberrations and our image, but instead of a library of different references, we have an instrument model with a guess for these aberrations. Because, you know, these are also imperfect, you will not get a perfect model at the beginning, but you can iterate through this process, right? You can have like a little feedback loop and iterate and solve for effectively accurate aberrations until you get, hopefully, a good match that can also be like accurate to the photon noise level in this case, by the way, though not necessarily, and you can actually find a planet. Now, of course, this is a very old and classic idea. You know, there's like some classic papers on this. There's a poster here, and I want to highlight also Natalia Sanchez's paper that is applying a similar concept in a different setting. But when we say solving for accurate aberrations, there's like more that goes into it, right? Because the model can be very complex. I want to get very high contrast. So if you want to do it right, you have to account for millions of parameters in your instrument model. And this is not something you can just like MCMC your way around, you know? You cannot just like scipy.optimize a million parameters, you know? So either we give up, or we look at the community that has been optimizing models with millions of parameters forever, you know, machine learning. And when they train neural networks with like 1 million or 1 billion or whatever, like parameters, they don't do it through MCMC, They do it through automatic differentiation. Basically, a framework to compute analytic derivatives through your model that speeds up by orders of magnitude what you can get. And this is basically what is behind, neural networks, and like you can also use backpropagation and GPUs and all these things, and that can get you very far. So if you plug in here autodiff or a differentiable modeling, then the computational cost is not that obvious of an impediment, and now it is worth asking whether we can do it. I want to highlight also that autodiff is like very hot right now, and like there's other works in this conference related to this. There's of course the Amigo framework, which Louis will give a talk after this, and he also has a poster, I believe. That's very, very interesting work. And there's a few other posters as well. I tried to get them all, but like the abstract book is like 100 pages, and like I had to get this talk done, so. But yeah, just like browse it, it's incredible how much power you can get from this. So I will show now some results on this using the NIRCam chronograph and real data from all of these experiments that I will be showing. So our model is basically what you might care about in NIRCam. You have something like, you might have some uncertainty on where the star is and how bright it is exactly in your filter. You may have some aberrations near the entrance of your telescope, from like mirrors and such. You will have aberrations internal to your instrument that you may not be perfectly able to characterize. And of course, you may have some detector effects, something like flat fields or brighter, fatter effect and things like that are not easy to model, but you can get a grip on them, with a pretty basic model. So once you have all this, you can pre-calibrate them on reference stars and then tune only some of them or your science target, and you can get pretty interesting results. So I will show 4 results that I think each one can teach you something different now. First, starting easy under quotation marks. This is HIP 60426. This is the first image planet we got from GWST. And it is a stunning detection, You can see like the diffraction lobes of the thing, it's really, really stunning, And you have something like an SNR of like 76.4, with clip and PCA. And this is a published reduction, so I'm not like handpicking PCAs, like Marcus might say, So when we run our model on this, we get something like this. We get pretty much the same PSF, but we don't get all the junk we have around it, And that's pretty, pretty cool, But again, this is a pretty easy planet. So let's increase the difficulty level a little bit. This is an example from what Aaron Carter surveys, where we have, again, a ton of different stars. You have not perfectly chosen your reference stars, to do PCA and things like that. And this is one of the candidates that he showed, that is, in one of the surveys. So for this, we use like 150 reference stars, and we get it like as nice as we can. The candidate is not confirmed yet, but like that is for sure an astrophysical source. And we get something like this, right? The blob is obvious, and we see like an SNR of 9. When we're on our method, the thing looks like Epstein DA. It's crazy. You have like diffraction lobes and things like that. And again, this did not require taking 150 reference stars, and you have a fully physics-based model for this. So even you can see with the error rings and such, and you can see that a lot of the little blobs that might worry you out planets may not be real after all. Now, let's increase the difficulty level a little bit more. This image that I showed before is actually a real data set from L. Bogat's paper. And this was basically a planet search program, through close associations. And this is a real published observation as well, And we don't get like very good contrast for a variety of reasons, right? Maybe the PSF the references were not very good and such, You don't see anything. But when you run our model on it, you have a big surprise. This is an injected planet. But it's still surprising, no? Because we injected the same planet with the same flux in here, but we don't see anything, And these are not even the same color bars, If you do the same color bars, it looks even more scary, So this might not be a real planet, but it is a real, like, tenfold increase in sensitivity on real surveys. And from these 2 examples, you can check what the potential for this is in exoplanet discovery. You remember the thing that Aaron showed? We have like hundreds of observations now in exactly this observing mode. So you can only imagine, maybe that planet was not real, but somewhere maybe, It is especially good for like the inner, like 2-3 arc second region, which is like, for these targets, it's like maybe like 20, 30 AU. And like, we don't know occurrence rates, but like, where are more planets, outside or inside 30 AU, you know what I mean? So I want to show one last example that I think is very illustrative. And we bring it back to one of the OGs of direct imaging, 51 REB. This is an observation, not with the round coronagraph, but with the bar coronagraph. And this was also a published observation by Will Ballmer, when they tried to constrain, some parameters in the atmosphere of 51 REB. The 4.3 micron line is especially interesting because that is CO2, and that is something you cannot get from the ground. And here, if you don't see where 51 REB is, it is because it was claimed as a non-detection. Again, there was some, the reference observations were not good enough. But when we run our method, and I will here suggestively change the color bars again, we get a pretty solid detection of 51 REB at 4.3 micron. To our knowledge, the first one that has been done. And again, this is a 4.3 micron, right? So you can get a lot of science from this, and like metallicity and all these nice things. So this is another example of like real science that could come from using this method that exists now on real observations. Now, I want to finish by showing just like 3 main things that I'm interested in from the future in this method. One, as I mentioned, this is a fully physics-based model, right? Which means that when we solve for this, we're not just choosing PCA modes, we are tuning physical parameters. So we might ask, well, can you learn about the instrument by doing this? So we applied this method to a bunch of different stars, and we are surprised that oftentimes this specific, for example, optical plane, just to pick an example, these aberrations look very similar. Now, because it is a very complicated optical system and like it's a degenerate and ill-posed problem, you can ask, well, are these like physical or are they, overfitting some other aspects or whatever, But what this is showing is that whether they are physical or not, they are systematic aberrations, which is telling us that this model is just not like super overfitting, into some like dark corner of parameter space, but it is getting something that potentially is reproducible and we can identify and correct for in our models. A different thing is that here we have the method diagram. And we see that at no point do we explicitly say, like JWST, You can put their Roman, you can put their Muri, And you can always fit a small delta on top of anything, So we may be able to apply this to other methods, to other instruments, and get very good results. And finally, having a differentiable model opens the door to applying all kinds of techniques of direct imaging and computational imaging and machine learning, I put here an image of a black hole image from the Katie Bowman's group here in Caltech that achieved, by using computational imaging, not actually an image, but a video of a black hole. Here, the presentation had to be in PDF, so I have a 2-frame video to show you. But the point is we can get very far, if we can image a black hole in another galaxy, with these methods, we might as well be able to image Earth-like planets or Sun-like stars. And that's it. Thank you.
Lots of questions. Here? Yeah.
Thank you for the great talk. I'm Ferrer-Chavez. Just a quick question. So for your model, how do you use actual spacecraft telemetry, and is it something?
Can you say that again? Sorry, can you speak a bit louder?
Can you hear me? Yeah.
Yeah.
Thanks for the talk. So for your model and the method you have, do you use actual spacecraft telemetry, and how important is it? Or for your model and these differentiable models, do you just go through all kind of search over all the parameters? Or how is it linked to what you already know from spacecraft telemetry, actually?
Yeah, so the way that we initialize models, we can do many things, but what we do now is that we take something like the STPSF models that are available, from Space Telescope, and we take that as like our initial condition, And based on that, we also have like, like every 2 days, like wave error measurements, that give us a good initial condition. And oftentimes these observations are taken, in a series, so we can pick one, that is like bright and nice or something, or they have like a dedicated reference star, and they can help for some calibration of these things. Obviously in the future we might want these properly calibrated so we can just forward model and get, photon noise limited subtractions and with no other issues.
Okay, time for one short question, one short answer.
Yeah, really great talk, Rodrigo. So I guess the question on everyone's minds are, what are the computational costs for doing this? How long will it take us to go through all these surveys?
Yeah, it depends on how good reference dart you have, how deep your observation is, and things like that. You know, for regular observations like the one I showed from Erin's survey, oftentimes you can get a good fit in like maybe 10 minutes or something like that. You know, and that is fitting again for like the whole plethora of like 2 million parameters. You know, ideally, again, after we go through enough of these and we have like a well-calibrated model, we will have a nicer optimization problem that could take, you know, minutes or seconds.
Okay, thank you very much.